Okay, here's a question that uses the idea of sort of Archimedes' principle. And it talks about you have a uniform rod wholly or partially submerged in the fluid, experience an upthrow equal to fluid displacement. So that's Archimedes. And show the statement is valid for the case of fluids and zeros. We're not moving. We're not going. That's more of a discussion one. I want to go for B and show what happens with this. Let me draw what's going on. The fishing float looks like this in effect. We have a mass at the bottom. The entire thing has a mass, and it floats in the water, like so. This is, of course, the density of the liquid, and it has not only a mass, but the object itself has a density. And it says the stick is depressed a very small distance and then released. Find the period of oscillation of the float. Ignore any motion induced by the liquid. So if this is depressed by, let's say, delta x, what then happens to the period of oscillation? Well, I think it's fair to say that the force which you'll experience is going to be the volume which of liquid, the extra volume of liquid you've displaced, which is going to be volume by the density by g, which is equal to the area times this small amount of length, density by g. Now, that tells us that the acceleration, which is the force divided by the mass, is going to be all that previous expression divided by the mass of both the bit at the bottom and the mass of the rod itself. Now, we know that, just on the side here, at equilibrium, when it's floating, the weight of the water should equal the weight of the float. So the volume times the volume that's submerged, which we will give an expression x naught, is going to equal to m plus m times g. So therefore we can say to ourselves the area times x naught, the area, or sectional area, times that length, which gives us the volume, times by that, and g should give us m plus m of g, therefore giving us an expression for the area, which is m plus m g divided by x naught rho g. Those drop out. So, therefore, we have an expression for the acceleration equals omega minus omega squared x. That's how we define simple harmonic motion. This gives us, we also know that the acceleration now is going to be, place that into there, so we're going to get m plus m over x naught rho of the water by x rho of the, sorry, that should be rho of the object, g over m plus m. Of course, the x's fall out, so we have an expression for omega squared, which is, in effect, m plus m rho g over m plus m x naught rho dash. We know that t is 2 pi over omega, so therefore that gives us 2 pi root the inverse of that, which of course is x naught over rho, over g, because those, are the same, which also cancel out. So the answer is 2 pi x naught over g. Sorry, there we go. Okay, the second part of this problem then talks about the stability of the float, and it asks that the upthrust acts on the centre of gravity of the displaced liquid. But of course this object has its own centre of gravity, and the couple acting on the float's axis is placed in the vertical condition. You need to satisfy this condition here. Okay, there's lots to get on with there. First of all, I suppose the first point is, the first hint we can use is to work out the centre of mass of the liquid and the centre of mass of the float. And once you have those two, then we're going to talk about the stability. Well, I'll give you the second hint anyway of stability. In order for this not to fall over, we want to make sure that the centre of mass of the liquid, G dash, centre of gravity, and G dash must be higher than G, otherwise it will turn over. And then the last condition that we need to bear in mind is it's not sinking. So therefore, x naught, which is how far it is below the liquid, must be less than the length of the object. So with those three hints, you can give this a go if you want. But otherwise, here comes the solution. Okay, first of all, right, so let's just draw that situation. There is the mass. Of course, we have the centre of mass, or the centre of gravity of the displaced liquid, and the object's centre of gravity. This is x naught. Let's say this is y. And good, yeah, so G dash is centre of mass of displaced liquid, and G is centre of mass of float. So let's work out where the centre of mass of the float is. So I do this by imagining if that were rolled over to one side, and this is the midpoint where the mass of the main float acts, and of course this is where the big mass m, the lead weight at the bottom, acts. Then if I were to take a point y, then it should be balanced if that is g. And I also know that this is going to be L over 2. So very simply, with a little bit of moments, I'll say to myself that m times y is going to equal m L over 2 minus y. And yeah, that's right. So let's do a bit of rearrangement then. So factorise the y out and drop it onto this side. So that means m plus m of y gives me L over 2m. And therefore y is L over 2 m plus m plus m. Okay, so that gives me a sense of where this is, of y. Now we said in order for it to float, we don't want the couple of these two, G dash and G, we don't want G dash to be any higher than G, otherwise it will rotate over. So we say G dash must be greater than G, the height. So where's this one? We know this is x naught over 2 because it's in the middle of the liquid that's displaced. So what we're saying is x naught over 2 must be greater than y, or x naught over 2 must be greater than L over 2 m over m plus m. Let's get that into shot. Good. Now what is x naught? Well, we can work out what x naught is because we know how how much liquid needs to be displaced in order to support this weight, a bit of Archimedes. So we can say x naught times by the area, it gives us the volume of the object and the volume of liquid therefore displaced. So if we take the volume of this is obviously the liquid, times g must give us m plus m g, something similar to that which we did in the past. So therefore x naught is going to give us m plus m where have I taken that from? We're going to take our area. Sorry, here we go. Do we remember from the previous bit that we said our area is going to be, sorry, wait a minute, not our area. Okay, so what is the area? Well, the area is going to be the area times the length times the density of the object gives us the mass. So that brings it back, and so we can say x naught is going to equal m plus mg divided by a rho g, rho dash g, which gives us m plus m. Get rid of the g's. Area is going to give us m at the bottom dash L rho at the top. Okay, so if we combine this one with this one, then that tells us that m plus m over m rho dash L rho over 2, let's just get rid of those 2's, it's going to be greater than L m over m plus big M. Okay, get rid of the m's. So what are we left with? M plus m squared rho is giving us, sorry, I forgot the rho at the bottom there, is giving us m squared rho dash. Or in other words, I have, looking back at this identity, I'm getting very close to what I'm after here on this side. So m squared over m I'm looking for, or squared should be rho over rho dash, which we have there in the first instance. So my first one's been satisfied. Okay, let's quickly move to the second one to be satisfied. And let's say that the second criteria was that x naught must be less than L, otherwise it would sink. So m plus m L rho over m rho dash, which we know before is x naught, must be less than L. So therefore rho over rho dash, get rid of those, gives me m over m plus m. So I combine those two conditions together with inequalities. Sorry, it should be less than, not equal to. Getting carried away there. Then what that should give us is rho over rho dash must be less than m over m plus m. However, must be greater than m plus m squared. Okay, there it is, done.